to our physical sciences. Today, my name is Temba Ngube. Our focus is on exploring electric fields. And, it comes from the background of understanding what an electric field is, in terms of the region, in space around a charge, wherein if we subject that charge to a field, it experiences an electrostatic force. But then the more emphasis on today's session will be around net electric field at a point, whereby we know that around a point charge there is an electric field, and then if we put a unit positive charge, it experiences a force in that field. Now we want to see, or explore rather, and discover some of the exciting scientific facts around net electric field at a point due to more than one charge, which is something that comes from understanding what exactly electric field at a point is, and also understand in as far as in terms of the big question in today's session, to say what exactly affects the magnitude and direction of electric field at a point. Right. Let's quickly look at the background in terms of what we already know. Okay, so we know something. Actually a lot about electric fields now. We can also indicate or represent the electric field patterns around a positive charge, around a negative charge. Also, when two like or opposite point charges interact, we can represent that field using the electric field lines. And based on that, we also spoke about, in our previous sessions, we have managed to talk about, the properties of electric field lines, right? This is very important because every concept in terms of the force, the vectors, is a result of the field. So remember the properties of electric field lines and how the Coulomb's law fits into the concept of electric field at a point, right? Remember, in an electric field, if we place a unit positive charge, we can get an indication of how strong the field is at that point. But it is purely based on Coulomb's law, and we managed to say that as long as we know the magnitude of the force that creates the charge, and we know that electric field at that point, due to a charge that creates the field, is equal to the Coulomb's constant multiplied by that charge that creates the field, divided by the square of the distance, right? So today we'll explore more about E net in terms of the net electric field at a point, right? And then the big thought about, or the idea that we need to be comfortable on in terms of, what we want to achieve. We want to also discover what are some of these important factors that affect the magnitude, okay, and direction. Already we're saying it's a vector of electric field at a point. So what exactly affects the magnitude and direction of electric field at a point, right? Now, having said that, let's look at the terminology. When you talk about the key terms or the terminology, these are definitions, which are basically all or nothing. So the language in science is purely grounded in the terminology. So we need to be very comfortable with the keywords in the definition, and we need to use the keywords in the correct context. That cannot be, emphasized even more, because we have always said that once you are given a definition, it's a all or nothing kind of a scenario, right? So the keyword that I want us to first unpack and maybe remind ourselves of is electric field at a point, which is a physical quantity denoted by uppercase E, right? E stands for the unit. This is the symbol of the unit of electric field at a point, which is the force experienced per unit positive charge, right? The force experienced, okay, per unit positive charge, okay? So remember, when you talk about a unit positive charge, you are talking about the unit of charge, which is +1 Coulomb, right? So this is the force experienced per unit positive charge, which is a vector quantity. So emphasis is on magnitude as well as direction, right? So the emphasis is on magnitude and direction. So this is one of the vector quantities. So, and we know that this E, the unit is Newton per Coulomb, okay? And we also need to emphasize on the direction, okay? And remember the significance of the unit positive charge in terms of the direction. So we'd also use the simulation just to show, try and simplify this concept so that we understand it a little bit better. And then the word net is very common in physics. When we talk about the net, we're talking about, usually we would say it's the resultant, okay? Sometimes we say it's the total, okay? So the word net means total. Then what exactly do we mean when we talk about net electric field at a point? We're talking about E net. So what we indicated earlier is that, we can talk about the electric field at a point due to a charge that creates a field. But then if there are multiple charges, then we can talk about a point and how strong the field is at that point due to those two, point charges in space. And then hence would refer to it in terms of the net electric field at a point, right? Okay, so that's as far as the definition is concerned. Very, very important, okay? So electric field at a point is a vector. That's the main idea. This is the science around it. Otherwise, what follows after that is just the maths in terms of the calculations. So E is a vector, so it's an indication of how strong the field is at that point. Say, for argument's sake, we've got a point in an electric field which has got a magnitude of 10, okay, newtons per coulomb, just for argument's sake. Okay, let's say this is E1 at point 1, and then E2 at a different point, let's say, for argument's sake, is half that, which is 5 newtons per coulomb, whatever the direction is. What that simply means is that the electric field strength, or the electric field at point 1, is such that the force experience is, this means that 1 coulomb of charge, okay, 1 coulomb of charge, okay, experiences a force of 10 newtons, okay? It experiences a force of 10 newtons, right? This is what exactly we mean when we say the magnitude of electric field at a point is 10 newtons per coulomb. So the unit positive charge, which is this plus 1 coulomb, experiences a force of that magnitude at that point. That's very important to actually bring an understanding into these figures or talk the science behind the numbers, okay? Now, equivalently, 5 newtons per coulomb at E2 would suggest that the force experienced by the unit positive charge is actually 5 newtons, which is half, or in the case of point number 1 in the same field, okay? Now, the force that will be experienced by a unit positive charge at a point due to a charge or multiple charge is the net electric field. So we are emphasizing the big idea around net electric field at a point. So this is, we identify a point in the field of more than 1 charge. Now, there are multiple charges, exerting a force on the unit positive charge at that point. So as a result of that, we can talk about the total or the combined effect of the forces exerted by the 2 charges at that point on the unit positive charge, which is our test charge, if we may call it that way, all right? So that's the big idea behind E net, which is primarily our focus for today, right? Now, say for argument's sake, X is a point, okay? So X is not a charge, it's a point. That's very important to make that distinction at a distance r meters from the charge Q, okay? So we've got charge Q, and then we've got a point X, which is a distance r from the charge Q that creates the field. So if the magnitude of the electric field at point X is 5 Newton per coulomb, okay? So E at point X due to Q1 at X, okay, is equals to 5 Newtons per coulomb, right? Whatever the direction is, okay? Now we just want to explore some understanding here behind the concept of electric field at a point. It says here, predict the effect of the following changes on the magnitude of electric. So our focus for now is the magnitude for now, okay? What if we're changing the distance to 2r? We double the distance. We want to understand exactly what happens. So I just want us to think about in terms of, at a basic level, if we double the distance between point X and the charge, what's going to happen to the electric field at that point, at the new point, which is twice the distance? Is it going to increase, decrease, or remain the same? So this is where we start. And then if we eliminate based on our understanding of the concept involved, I think then we are able to say, okay, then definitely if we increase, we expect it based on the mathematical relationship. But before we do that, let's look at a simulation just to give us an idea of what it means to double the distance, right? Okay. So we have a scenario here, okay? We have, let's use any type of charge. It could be a positive point charge, right? So around that positive point charge, what do we have? We actually have the electric field, but this electric field in this case is actually away from the charge that created the field. So that's the direction. So if we put a unit positive charge at some distance, that's what is going to happen. It will be repelled away from that charge which created the field. Now the issue here is about distance. Let's say for argument's sake, okay, let's say for argument's sake, we double this is the initial distance. Okay, that's our tape measure there. Okay, the tape measure says, okay, okay, sorry.
I tried, sorry.
It's fine.
You can just go back to the tape measure.
Okay, should I go back?
I don't know, Oscar?
No, it's fine.
Sorry, guys.
It's fine, Colin.
Yeah. I sneezed. I'm sorry.
Okay, we start on top of that.
That tape measure.
Should I start on top of this?
It's fine.
Yeah.
Tape measure?
Yeah, you can start from
Yeah, you can reset it.
From the tape measure?
Yeah.
Yeah, reset it.
Okay. Is it fine like that? I want to start here. Or should I, is it fine? Okay. All right.
But 4 minutes.
Left?
Yeah.
That's fine. Okay. On your count?
Okay, 3 to enable 1.
Right. Now, this is the direction as indicated by the tail head, of the force that the unit positive charge will experience as a result of the charge that creates the field. Now, I'll measure the distance roughly. Okay, here's our tape measure. Okay, I'll try to measure that distance. Okay, something close to, okay, like 73.2 centimeters. Now, if we double this distance, what are we expecting? We're expecting something in excess of what? 146 or 0.4 centimeters, which is 73.2 as an example. Okay, I'll remove that. Let's move that further away. You can immediately see what is happening to the length of the tail, which suggests something about the what? The direction, about the magnitude, right? 146, something there, or 145, 144. Okay, if I put it there, you can tell already if the distance is doubled, the magnitude of the force experienced by the unit positive charge decreases. Okay, but it should be informed by some form of mathematical relationship that exists between electric field at a point and the distance. Okay, going back to our question. Now we have doubled the distance. What do we know? We know that E is equals to K, Q over R squared. So if the force, if the charge is Q and the distance is R, what have we done now? We have doubled the distance. So we are told that this is 5 newtons per coulomb, okay? Right? So this is 5 newtons per coulomb, in other words. That's our magnitude of E, which is electric field at a point. So if we double the distance, what happens there? We get the new force in terms of 5 is going to be K, Q, because the charge is still the same, we've doubled the distance. Now we are squaring that double distance to give us k q over 4r squared, right? Immediately I can tell, okay, now this is like a quarter of k q over r squared, of which we know that this is represented by 5 newtons per coulomb. So already we can tell that this is a quarter of 5 newtons per coulomb, which is 5 over 4 newtons per coulomb. Now already you can tell that the force experienced by a unit positive charge actually decreases, right? So if we change the distance, the new force would be 5 over 4, okay, which is like 1,25, okay, which is a quarter of that. So it's going to decrease to 5 over 4 newtons per coulomb. So neither does the force increase or remain the same if we double the distance. The force will actually decrease, but it's in proportion with the mathematical relationship that we already know. So this is just a basic idea in terms of how does the distance from the surface of the charge that creates the field to the point in the field, how does it affect, when we vary the distance, how does it affect the magnitude of electric field at a point? That said, let's take a short breather. We'll explore more of these, manipulations as we go ahead. Let's take a short break for now. Welcome back to our second segment. We're still looking at exploring electrical fields at a point whereby we have got multiple, charges that create the field, and the common point which is in the field of both. But before that, let's look at the mathematical relationship that exists between, varying distance, the charge, and how exactly that affects the magnitude of electric field at a point. Now, question B says, predict the effect of the following changes on the magnitude of electric field at point X. Now, we are trebling the distance, so language is very important. So if we treble something, it means we multiply it by 3, or it becomes 3 times as bigger, all right? So if we go back to our simulation, right, we obviously use the very same. So it means the distance even becomes greater. So instead of that 144, we make the distance 3 times as greater, all right? So if that is the case, you can see already the magnitude of the electric field at that point gets smaller and smaller. So in terms of our, basic question, if we treble the distance, make the distance 3 times as bigger, the original distance, does the magnitude of electric field at a point increase, decrease, or remain the same? So it starts with that multiple choice. Obviously, if we're seeing that, okay, the further away we move from the surface of the charge, the smaller the magnitude of electric field at the point becomes. So that's the important thing that we also want to highlight there, right? So having said that, let's look at the case, because we're told that at point X, if it's R, it's 5 newtons per coulomb. It means if we treble the distance, the magnitude of electric field at point X 3 times the original distance away from the surface of the charge would be even smaller than 5 newtons per coulomb. Okay, what does that mean? It says here, we know that E is equals to KQ over R squared, okay? Now, in principle, we know that this, we are told that it's equals to 5 newtons per coulomb in magnitude, right? So what is important for us is to understand that E and the distance are actually inversely proportional to each other, or E is directly proportional to the reciprocal of the square of the distance. So we'll arrive at trying to sketch a graph that represents that particular relationship. So if it's 3 times as big, what do we have in terms of 5 newtons per coulomb? So it should be in multiples, but do we multiply by a factor that's greater than 1 or less than 1? So if it's going to decrease, it means we multiply by a factor that is actually lesser than 1, which is a fraction, okay? So we'll have K, Q, still the same charge, divided by 3R. but we square 3 times the distance, the original distance. So what do we have here? We have k q over 9 r squared, okay? So I think we're onto something here. We already say it's a ninth of the original electric magnitude of electric field at a point, because we know that this is 5 newtons per coulomb. Then this reduces to 1 over 9, which is 5 over 9 newtons per coulomb, okay? So this is the new magnitude of electric field at a point, which is actually lesser than when we double the distance. So if we can go back to that question and actually say, okay, what is the magnitude? It's 5 over 9, right? 5 over 9 Newton per coulomb, that's the magnitude. We didn't say anything with respect to the direction. What about if we make the distance 4 times as big? We need not go back to the simulation now because we've picked up the pattern. So if it's 4 times as big, what are we saying here? We are simply saying that it's going to be kq over 4r squared. So we're squaring 4r. So this is like 5 over 16, okay, newtons per coulomb. So it's even smaller and smaller. Now, we can arrive at a point where we say, okay, so if that's the case, so we've used the PhET simulation as we have shown earlier. So we are saying that one of the factors that affect the magnitude is actually the distance. So we've realized that electric field at a point, this is our E, right, is inversely proportional to the square of the distance. Hence, we are saying E is inversely proportional to the square of the distance, right? So this is the mathematical relationship that we were trying to explore, right? So let's understand that. So but this is only true if we keep the magnitude of the charge constant, okay? So this mathematical relationship of if we increase the distance, what happens to E? If we decrease the distance, what happens to E? Can only be true if we only vary the distance and keep the magnitude of the charge that creates the field constant. Now, this takes us to something that is very, very critical in terms of scientific inquiry or, you know, experiments, investigations, where we talk about variables, okay? We've got 3 types of variables, just as a reminder. We've got the independent, the variable that we were manipulating or changing, right? And then we've got the dependent, which is the response variable. So once again, in this particular exploration, we looked at varying distance or changing the distance from the surface of the charge and seeing how it affects the magnitude of electric field at that point. So wait a minute. So if we change the distance and see how it affects the magnitude of E, we are saying the distance is the independent variable, while electric field at a point is the dependent. What did we keep the same? Okay, we did not change the magnitude of the charge Q. So the magnitude of charge Q was actually our controlled variable in this case. Hopefully it makes a bit of sense, okay? Now, if this is the mathematical relationship, now we want to sketch a graph that shows this relationship. So we've already identified our variables, and we know that for a graph, there are very important components of it. Number 1, the title, which is E versus R squared, all right? This is what we are saying. Okay, so on the vertical axis, we've got the dependent variable, which is E. We must also indicate the units of E. The units of E are in Newton per coulomb, right? And then on the horizontal axis, what do we have? We've got the square of the distance, all right, which is R squared. This is in meters squared, right? Those are the units of our independent variable. So this is the mathematical relationship that we managed to obtain. All right, but then one may say, okay, what if we talk about the relationship that exists between E versus 1 over R squared, okay? So 1 over R squared and E are actually directly proportional. So we'd have something of this sort. So we've got our E, once again, in Newton per coulomb, okay? And then we've got 1 over R squared, okay? This is per square meter, okay? Those are the units. Take note of that. And then there is a linear relationship between those two. So we need to be very comfortable as far as understanding, because the whole concept is about these relationships. So as long as we are comfortable with that, we are able to make predictions as we demonstrated in the previous question, right? Okay, and then it goes further now. We are onto something a little bit different. Okay, let's try and see what exactly and how unique is this scenario different from the previous one. X is still a point. I'm going to highlight that because there's a major issue regarding, a point and a charge. There's a point charge in space. What exactly do we mean by that? We're saying at a certain point in space, at a certain position, okay, we've got a charge, all right? And then if we place a charge, we call that charge a point charge, okay? And then we can top of a point in the electric field, it's X. There is no charge there. It's just a position relative to the charge that creates the field. So that needs to be kind of very clear from the onset, right? So X is a point that is still at a distance R, okay? There's charge Q. We assume that charge is going to create a field, right? If the magnitude of electric field X is 5 newtons per coulomb, so we're saying E at point X, or E due to Q at point X, is equals to 5 newtons per coulomb. Once again, that's the magnitude, okay? Whatever the direction is, for now, we're not interested in that, okay? But remember, electric field at a point is essentially a vector quantity, right? So it says here, predict, again, predictions, and more predictions. And these predictions, as we have grown to understand it, they essentially talk about the relationship that exists between physical quantities. So now we are exploring the effect of changing the magnitude of the charge versus the electric field at a point, okay? Now it says here, predict the effect of the following changes on the magnitude of electric field at point X. Now, we double the magnitude of electric charge, okay, Q. So if we double the magnitude of Q, so we have E is equals to K, Q over R squared, right? Now, nothing was said of the distance, so we'll keep the distance the same. Okay, so we know that this E is actually equals to 5 Newton per coulomb in terms of magnitude, okay? But now, if we double the charge, the question that remains, basics, does the value of E at that point increase, decrease, or remain the same? That's the line of thinking that we want to assume or want to use. So if we double the charge, does the field become stronger? Definitely does. So at the same point, using a bigger charge, we actually have a case whereby the force that a unit positive charge experiences becoming, correspondingly greater, right? So if we double the charge, what effect do we have there? We then will have K, 2, Q, that's the doubling part, okay, over R squared, okay? So this is like 2, okay, K, Q over R squared. So this is actually double 5 newtons per coulomb, which is equals to 10 Newton per coulomb in terms of the magnitude. So once we double the magnitude of the charge or increase, so doubling is essentially increasing the magnitude of charge, okay? So a bigger magnitude of charge at the same point will have a stronger electric field at the same point, right? So that's exactly what we're talking about. Now, if we have it, it means, again, corresponding, I think we get the trend now or the pattern. So if we have it, what's going to happen? The magnitude of the electric field at a point will also decrease. Having is a decrease. So that's where it all begins. So a decrease in the magnitude of the charge that creates the field correspondingly or consequently would affect the magnitude of E by also decreasing it, okay? Are we onto something here in terms of the pattern? And then C says, making the charge Q 3 times as bigger, okay? Now, if it's 3 times as bigger, it means the also E will be 3 times 5. So here is gonna be what? Half the original one, which is gonna be 2.5 or 5 over 2 newtons per coulomb, okay? You don't need a calculator for that, okay? And then making it 3 times as bigger is gonna be 3 multiplied by 5, okay, newtons per coulomb, right? So if that happens, then we get 15 newtons per coulomb, right? So what are we on about here? We are saying that the mathematical relationship that exists is that once you increase the magnitude of the charge that creates the field, at the same point, the size of electric field at that point will be correspondingly greater, right? Having said that, we'll come back after the short break where we'll look at, the actual concept of E net. Let's take a short breather for now. Welcome back to our third and final segment. We're still talking electric field at a point, but now we just want to focus our attention on net electric field at a point. But before we do that, let's quickly look at the mathematical relationship between electric field at a point and the magnitude of charge. So we are saying that E is directly proportional to the magnitude of the charge, okay, provided we keep the distance from the surface of the charge that creates the field constant. So once we do that, we know that when we increase the amount of charge, we use a charge that's bigger, so the value of E will also increase. So electric field at a point is directly proportional to the magnitude of the charge that creates the field. But remember, direct proportion, it means if we increase the charge, the value of E will also increase in the same proportion. So what that simply means, from our sketch of the graph, we've got E versus Q, right? Okay, this is just a sketch just to show the relationship, okay? So we're changing Q, okay? Q is in coulombs, right? And then on the vertical axis, we've got E, which is electric field at a point in newtons per coulomb, right? So this is the relationship that exists between those two, right? Let's shift our gears a little bit and look at net electric field. Now, determine net electric field at a point due to two charges. So we're talking about an E net in this case, okay? Right? So E net is a combination of, two charges. We've got a common point which is in the field of both charges, and then we want to know what is the effect on the unit positive charge at that point due to the two charges. So the 2 point charges are 6 centimeters apart. That's the distance between the 2 point charges, okay? And B is the midpoint, okay? Midpoint, it means B is equidistant from Q1 and Q2, right? Then calculate E net of the field at point B. So the E at B is due to, let's call this one Q1. Let's call the 3 microcoulombs Q1, and then let's call the negative, let's label the negative 1 microcoulombs Q2, right? So this is the scenario that we have. Right, let's do the science. Now, at point B, we place a unit positive charge, okay? There are two charges exerting a force on the unit positive charge placed at point B, right? So at point B is a point. Let's get that clear. So at point B, let's put a unit positive charge there. That's a free vector diagram that we want to come up with, okay? So I've used a dot. It will be a free in the form of a free body diagram. So the unit positive charge that is placed at point B is positive. Now Q1 is also positive. So the force exerted by Q1 on the unit positive charge placed at B is in that direction, right? So we'll call that E due to Q1, right? So that's the direction of the E at point B due to Q1. Why is it in that direction? We've demonstrated that using the simulator, okay? What about the force experienced by the unit positive charge at the same point B due to Q2? Now, Q2 is negative, so it will exert an attractive force on what? On the unit positive charge. Then we've got our E due to Q what? 2, right? So this is our vector diagram. Now, this vector diagram will be very important in terms of the direction, okay? So E net, in this case, becomes equals to E due to Q1 plus E due to Q2, right? So we'll say because both of them, these vectors are to the right or towards Q2. So we'll take that direction as positive, okay? We're choosing our direction. The direction towards Q2 is positive, okay? So if we do our calculation of E net, we'll have our E net is equals to K Q1, okay, over R squared plus, the plus in this case is for the net, plus K Q2 over R squared, right? So we're still using the formula that we're very familiar with, okay? Now, if we carry out our substitution for E net, we'll have something of this sort. E net is equals to 9 times 10 exponent 9, okay? Wait a minute. The magnitude of Q1 is given in microcoulombs. So we need to carry out the necessary conversions before we substitute into the equation. So if we convert microcoulombs to coulombs, it will be 3 times 10 exponent negative 6, right? The square of the distance is 3 centimeters. So we need to convert 3 centimeters to meters, which is 3 times 10 exponent negative 2. We square that distance. So this substitution is for E due to Q1. What about E due to Q2? So this is plus E due to Q2. So we do our substitution, 9 times 10 exponent 9, right? Multiplied by our value for the charge Q2. Now we'll ignore the negative because it will mess up our direction because we've used the vector diagram to determine E due to Q2, which is saying to the right. So if we put a negative there for the magnitude of the charge, it's going to mess up our direction. So that's the main thing in as far as determining E net. So this is 1 times 10 exponent negative 6 over the square of the distance, which is the same 3 times 10 negative 2, and then we square that distance. Now, what remains after that is basically the maths, okay? So we can go to our calculator very quickly and then try and get that value quickly because we've managed to do our substitution, okay? So actually, all the science has been done here. What remains is for us to determine the value of E net, right? So this is the scenario that we have. Let's calculate the first E due to what? Q1, which is 9 times 10 exponent 9, okay? Multiplied by 3 times 10 exponent negative 6, okay? Right? Divided by 3 exponent negative 2. Maybe we need to square that, right? Let's put it in open bracket, okay? 3 times 10 exponent negative 2, okay? And then we square that. So what you see there in terms of what we have punched into the calculator, it would give us the value of E due to Q1. Okay, but we know that it's the sum because they're in the same direction. We put another fraction, okay? 9 exponent 9 multiplied by 1 times 10 exponent negative 6, okay? And then we square the distance, same distance, because we're told that they are equidistant, which is 3 times 10 exponent negative 2. Okay, we close that and we square the distance. So if we pass the equal to, it will give us the value of E net. So if you count there, 1, 2, 3, 4, 5, 6, so it's 40 million newtons per coulomb to the right. So this is 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 zeros. So our E net, right, just to go back to that, okay, our E net is equals to 40 million, which is 4 times 10 exponent 7 Newton per coulomb. This is the magnitude, but the direction is towards Q2 or to the right, okay? Or to the right. So this is how we determine the magnitude of E due to 2-point charges at a common point, right? So there's a lot of things. Just to go over it, we need to use the vector diagram because we've emphasized the vector nature of E due to a point, at a point due to 2 more than 1 charge, okay? And then here is the vector diagram that I was talking about. So we managed to come up with that. E due to Q1, okay, that's the signs, and then E due to Q2. They're in the same direction. Okay, let's change gears and look at something different. The net electric field at a point, okay? 2-point charges, we've got Q1 and Q2, right? Which are 30 centimeters apart, okay? And then P is a point that is 10 centimeters east of charge Q2. Direction, direction, and direction. So the moment we see that, we can no longer use left and right because it's prescribed for us that we'll take, because these are collinear. Q1, Q2, and point P are collinear. It means they fall on a straight line, okay? So towards P is east, towards Q1 is the opposite, which is west. So if we can say, for argument's sake, from the onset, okay, naturally I would choose, because I'm right-handed, I'll choose east as positive, but it doesn't have to be like that. So we'll take this one as positive, or as an example, okay? Now use a vector diagram to determine the electric field at point X, but we are talking about the net electric field at point X. So what are we looking for here? We're looking for E net. How is this scenario different from the previous one? The three are collinear, the two charges and the point. Now, first we've got the two charges, and then point P is to the right of the two charges. That's the main difference, okay? So if we were to do our vector diagram, okay? So here is our point P, okay? There is our point P. I'll just do it just next to point P just to illustrate the vectors, okay? Now, Q1 is positive, right? Q1 is positive, while Q2 is negative. So E due to Q1 at point P. So if we place a unit positive charge here at point P, due to Q1, it will experience a force to the east because those are like charges. So this is our E due to Q1, right? That's our vector, first part of the vector diagram, okay? And then E due to Q2. Q2 is negative, while the unit positive charge is positive, as the name suggests. So in which direction will it experience a force? It will experience a force westwards. So this is E due to Q2. But I also need to just highlight something. These are just sketches. This is not a scale diagram. When we draw the vector diagram, we're not necessarily indicating that this is the actual magnitude. For us, it's just to get a sense of the direction. So this is not a scale drawing. So whether the tail is longer or shorter, the emphasis is on direction. Remember, it's the vector nature of the quantity electric field at a point, right? So this is our vector diagram. So if we were to determine E net, then the mathematics follows. E net is equals to E due to what? Q1, okay, plus E due to Q2, right? So the plus suggests something about the addition, the resultant, the sum, which is the net, right? And then E due to Q1, now we know the formula. We can go straight and say 9 times 10 exponent 9, okay? That's the K, multiplied by 3 times 10 exponent negative 6, that's the microcoulomb, divided by 30 times 10 exponent negative 2, okay? We square that distance, right? Plus, okay, but the plus here, it's for the sum. But then E due to Q2 is westwards, which is negative for the direction, okay? 9 times 10 exponent 9 multiplied by 5. Remember, we ignore the negative, because if we say minus, minus is going to be plus, and it would be as if E due to Q2 is also eastwards. So we would ignore the negative sign of the charge and consider the direction because it's a vector, right? 5 times 10 exponent negative 6, okay? Divided by the distance. How far is point P from charge Q2? It's 10 centimeters. So it's going to be 10 multiplied by 10 exponent negative 2. We square that distance. So this is what we're going to get for our E net, right? So our E net in this case becomes, then we can go to our calculator, right? So from our calculator, we are immediately able to say, okay, there are two sides to it. It's going to be 9, or we put that fraction because that's what it is, a ratio. 9 times 10 exponent 9, which is the k, multiplied by 3 times 10 negative 6, which is actually the magnitude of charge of Q1, okay? Divided by, let's put that into brackets because our intention is to square the distance. So that's going to be 30 multiplied by 10 exponent negative 2, okay? We'll square that as well, okay? Minus is for to say E due to Q2 is in the opposite direction of E due to Q1. Remember, net takes into account the direction because these essentially are vectors, right? So 9 exponent 9, that's the k value, multiplied by the 5 times 10 exponent negative 6, okay? We divide that by the distance, which is 10 multiplied by 10 exponent negative 2, okay? Which is, we're changing those centimeters or converging from centimeters to meters. Do not forget to square the distance, okay? So this gives us the value of our E due to those 2-point charges at point P. So this is like negative. A negative says it's actually west in terms of direction, okay? Because we said that if towards P is east, which is positive, then if the answer is negative, our interpretation of it is that it's going to be westward. So how many zeros do we have here? 1, 2, 3, 4, 5, 6, okay? So it's 4.2, okay? Okay, it's actually negative 4.2, which is 4.2, okay, times 10 exponent 6 Newton per coulomb. Then that negative suggests that the direction of net is west. So that's the magnitude, that's the direction. All right, now in closing, in summary, we understand that electric field at a point E is the force experienced per unit positive charge. That's straightforward, okay? It's a vector, we know that, and the field is directly proportional to the magnitude of the charge. So these are some of the legal detail that we need to remember, but the science around problem solving needs to be consistent. Electric field at a point, net electric field at a point are both vectors. So there's an emphasis on direction, direction, and direction. Having said that, let's try and say, okay, if a question is given, you need to do the science first. The science is dealing with the vectors. Because of time constraints, we've reached the end of our session for today. Hopefully you take something out of these discussions. For myself, it's goodbye for now.